And there was a button here somewhere. Use sound from computer.
Yes, when you click on share screen,
Okay,
you have the option to select the share computer sound. Yeah.
Okay, that's good.
Yeah, that's good to do if you're sharing a movie, or that way the sound comes straight from your audio. Okay, I'm going to be posting online to make sure people know that we're going to be live there. Super excited.
Okay, actually, I didn't try the chat because yesterday
there is the Q&A option, the chat by default. I can enable it for you if you want.
Yes, try to enable it. So if I do a share screen, if I start the presentation, for example, right now, I'm not able to see the chat window. One way or another.
Not the chat. You weren't able to see the chat window with the presentation. But Mihai, will you be on, or I can help?
Yes.
Now, are you saving all the questions for the end of the presentation, like yesterday?
No, they also can put questions in the meantime. There's no problem.
Okay.
Let me see if I hear.
Keep an eye on that too. I'll watch.
Post sharing Q&A. No open question. Answer dismissed.
Yeah, so theoretically the Q&A option, it should be easier for us to track the questions and answer them. But I have also enabled the chat. So if it is needed, then so put information on the chat.
I don't know here, probably you see right now my screen. I don't know here where the chat button is.
It should be right next Q&A. Or
next
I think, but you are sharing the screen, so I think you have to exit the full screen.
But that's what I wanted. I wanted to have the chat window while sharing the screen.
If it is full screen,
it is full screen.
I mean the Zoom window. If it is a full screen, you won't be able to have also the chat. But if you exit the Zoom window from the full screen mode, you will still have the presentation as full screen. But I think you will be able to see also the chat.
Okay, so then I have to exit the.
Or you can click on the menu, I think up or down. I don't know where it is for you. You have a view option.
I do have a view options. More.
And
computer. No.
Is side-by-side mode or zoom ratio, which is then could be changed for different sizes, and maybe will allow you to see the application.
No way. So, but I see Q question and answer, but I don't see the chat window. Okay, so if I stop sharing, one moment.
Chat with.
If I stop sharing, or if I stop sharing, I do see the chat window.
Exactly.
Because it's embedded in the software.
Yes,
and now, if I share the screen, and then I share computer sound, but then the thing is going to disappear.
Yeah, indeed, the application per frame is going to disappear, but you can share not the full screen, you can share just the application, just the presentation. So in this way, I think you will be able to keep the window not on the full screen on your display.
Okay, now I shared only the PowerPoint
and
application.
It's the same as earlier, which is okay.
Okay, which is
and you are able to see also the application frame. If you go to view option, try side-by-side mode.
View options, it doesn't matter, we can just start.
Okay.
We'll keep an eye on the chat and the Q&A.
Yeah. Okay, so I will just stop share from the beginning. Okay, so in principle, I'm ready.
I think we can start. I'm just publishing also the live streaming Facebook.
Yeah. And welcome back. This is day 2, and we're looking forward to our discussion today. It was wonderful to learn about the dwarf stars, white stars yesterday, and so we're back for more.
Okay, nice to see you again.
Nice to see you.
Yes, the same basically as yesterday. I just want to warn you, if I disappear very quickly, it means I have a crash on the computer, but I prepared a different laptop, so don't worry. I have here a presentation. Yesterday we talked about white dwarfs, today about neutron stars, supernovae, and gravitational waves. I will share the presentation, but first let me show you the book. So for the Romanian readers, this is the book, and here you find basically the fundamental physics, all the physics, I mean all the fundamental physics, quantum mechanics, string theory, Higgs bosons, whatever you want. It's just here, it's a big book. As I told you yesterday, I'm a physicist, I have a PhD, but in solid state matter. So I'm not an astrophysicist, but for sharing physics, general physics, yeah, it's kind of okay. It's also very nice. So let me share the presentation. So if I say share screen and I say screen 1, so now you should be able to see my screen. Okay. So are you able to confirm that you see my screen?
Yes, we see your screen.
Okay, great. As yesterday, these are the books. This is my YouTube channel. If you want to see videos, some of the videos have English subtitles, so they can be seen. Actually, I added this nice book. This is from my second book. Somebody illustrated all the planets in the solar system. And I find it such a nice drawing. So this is drawn by hand. This is not computer animation. This is just drawn by hand. You see how
beautiful.
Exactly. If you look at Jupiter, it's nice, very nice, makes you dream.
Yeah. Wow.
This is the slide I showed yesterday, and I'm going to show today as well, and tomorrow as well. And I made here the laser pointer, which is red, kind of difficult to see here, but it's here more or less. And yesterday we discussed that when you have a lot of hydrogen gas around, then it starts to come together because of gravity, and it's going to initiate a star. And the star is going to grow. On the top part, you have the normal star, which we discussed yesterday, like the sun, which is a yellow dwarf, becomes a red giant, then it sheds out the outer layers, and in the middle, you are left with a white dwarf. And then at the end of the universe, it's going to become a black dwarf. That's what we discussed yesterday. And the white dwarf is a star which has the mass of a sun approximately or smaller, and then it is the size of the Earth. Now we are coming back to the second part, which is here. Now what happens if the initial star is larger? Because if you have a larger lump of material, a larger lump of hydrogen, then the stars which forms is going to be larger. And that's what you see here. You see here a big blue star. Now it's drawn blue because if the star is larger, then the gravity is going to push on the center, and there the temperature is going to be also larger. And we learned yesterday that if the temperature of the star is higher, then the star looks bluish. So that's why when you look at the star, you see blue on the sky in the evening, you may say to your beautiful girlfriend or boyfriend, what a beautiful star. But let me tell you more. It's blue, it means it's hot. Okay, but also this blue star, which usually lives less time, because the larger the star, the higher the temperature and the faster it burns. This also has a life cycle. And at the end of the last life cycle, this star is going to shed as well the outer layer. So instead of becoming a red giant, like the sun, is going to become a super red giant, even a higher one. And now things becomes very, very interesting, because the core comes together, and the core is going to form, in the first instance, a white dwarf, but then the core is going to implode. We are going to see today. And then the core, at the end of the day, is going to become something else. But the interesting part is that the fact that you have an explosion in addition. So in other words, at the end of this super red giant phase, there is a huge explosion, which we call supernovae. And it's a supernovae of type 2. Yesterday we discussed about the supernovae of type 1. This is supernovae of type 2. But after this huge explosion in the center, you are left with either a neutron star or a black hole. So this we are going to see today. We're going to talk about the neutron stars. Now let's see first a very nice supernovae explosion. Hopefully it's going to have the sound. If I do this. This is a supernovae explosion. You see, it sheds out the outer layers. These are the outer layers which are pushed by the inner part. So the inner part already exploded and it's pushing the outer part aside. And of course, this is animation because we didn't see that up to now in real time. But that's how we imagine it is. And then at the end, just in the center, we're going to find either a neutron star or a black hole. See, we found a black hole, which sits at the center of our star. So what happens, actually I'm going to stop sharing the screen so that you can see me better. So now you see me better. Yes, Peter? Okay. What happened? Well, the point is the following. The evolution of the star is given by the initial mass of the star. The stars like Sun have lower masses. This way they are called dwarfs, yellow dwarfs. And the core, which is left, it's smaller. And these masses, the stars ends as white dwarf. But if the initial star has a mass which is higher than 8 solar masses, then it's going to let a neutron star at the end. But if the star is even higher, than 12 solar masses, then the core which remains is not a neutron star, but it becomes a black hole. And everything happens because the initial star was very high. That means large, but also the core of the star is very large. And because the core of the star is very large, then it's going to push harder and harder and harder, and the core collapses. Let's say that's the most important mechanism you have to remember. If the core is very large, it's going to push together higher and higher and higher. And the larger the mass of the core, the more is the chance that the core is going to implode. So in the beginning, it implodes, becomes a white dwarf. If the core is even larger in mass, then the gravity is larger and the core implodes smaller, it becomes a neutron star. And if the mass is even larger, the initial one, larger than 12 solar masses, then the core explodes even further and becomes a black hole. So let's see now a different animation with a supernovae. So this is after the explosion. So you see here the light of the explosion. Oops. You see here the light of the explosion, and now you see the outer layers, which are pushed. And I'm going to switch a little bit to the physics. Coming back from the animation, I switch a little bit to the physics to try to explain you. Okay. One moment. Okay. To try to explain in my words what is happening inside the core of the supernovae. Well, actually, I can show you. Let's show also the slide so that you know more or less what happens. Let's say this is the most difficult part of physics, and then we are going to have more animations. Yes. So bear with me like 5 minutes because the physics is so fascinating. So I'm going to talk actually what I wrote here, what happens. And I'm going to talk because I try to imagine what it happens inside of a core, which of a star which explodes like supernovae. What does it really happen? I want to be there. I want to be sure, to see what happens. So again, we start with a star which is large. So the star has masses which are larger than 8 solar masses, and the masses are distributed, outside. But the most important part is the inner part, which we call the core. Why is that important? Because the core suffers the gravitational pressure of the outside layers. And because of that, the core becomes hotter and hotter and hotter, and it starts to fuse. The temperature increases, and it starts to fuse more and more elements. If initially you would have the white dwarf, and the white dwarf would have only carbons inside, now because the outer layers of the core this time, because they push so hard on the inner part, then the temperature increases even more, then the carbon starts to fuse. So then you obtain oxygen. The oxygen starts to fuse, and you obtain neon, and then you obtain magnesiums. You see this kind of 4-step layer in atomic number. That's because by fusion, you add extra alpha particles. Alpha particles have 2 neutrons and 2 protons. So in the core, you fuse these elements like by 4, by fusing alpha particles. A little bit outside the core, you fuse also other elements. So this is basically this. So let's switch a little bit to the video, okay, to me, because it's important. You have to remember that the core of the supernovae is actually the only laboratorium we have in the universe to create heavy elements. Because at the Big Bang, we had only hydrogen, maybe a little bit of helium and a little bit of lithium. The world would not be without supernovae as we know it. We wouldn't be, the planets wouldn't be, because we all need atoms which have higher atomic numbers, like calcium, oxygen, potassium, whatever you love to eat sometimes. Think about that. Huh? And all these higher elements are actually produced inside of the supernovae. The thing what I have here, for example, I have a ring of gold, half of this gold in my ring was once part of the core of the supernovae. Now, the other part of this gold was actually part of the fusion of two neutron stars. But that is going to come at the end of the presentation. Somebody calculated that. Yeah, somebody
pretty
calculated
amazing to
that.
Think about. Makes it
somebody did these calculations,
Yeah.
So when you give it to a girl and say, look, I give you something which was once inside, the half was inside of the supernovae, and the other half was once inside, of the fusion of 2 neutron stars.
A whole new level. Wow.
Exactly, yeah. So then you have this element. So let's go back to my presentation here, so that we follow this line here. And then you fuse all these elements, but there is a point. You fuse them until iron. And at iron cannot be fused anymore. Iron cannot be fused anymore. And actually, if you try to fuse iron, you eat up energy from the surroundings. You eat up energy from the surroundings. Now, what happens when you eat up the energy from the surroundings? That means you cool the inner part. And the inner part, which was hot, and because it was hot, it had a higher pressure, and it was keeping the outer layers from collapsing, because the pressure was very large, because the temperature was very large. It was keeping the outer layers from collapsing, because outer layers want to collapse because of gravity, but this heat inside kept that. Now you have immediately iron, and iron, when it wants to fuse, it keeps it takes the energy. So it takes the energy from the surrounding, it cools down the core doesn't have any more temperature, and what happens? The outer part of the core starts to collapse even more. And that's the key part. That's the key part. Everything starts to collapse because there is nothing inside which can keep the gravitational pressure. And when the thing starts to collapse, so I will switch now again to the screen so that you follow. So now one moment. Now I am here, you know. Let me show you where I am. I'm here, you know. So when the outer part of the core, you know, starts to collapse, it goes inside, it becomes smaller and smaller and smaller, and then you have the atom, which is formed by electrons going around the nuclei, going around the proton and neutrons. Now what happens, the electron starts to become closer and closer and closer to the protons, and they start to fuse. And they start to fuse with the protons. So the protons and the electrons fuse, and they give neutrons. You know, that's why we have neutron star. Neutrons and neutrinos. Neutrinos are smaller particles. And then neutrinos fly away. They just fly away. And then the last part happens. One moment. Okay. And now the last part happens, which is the explosion. And this is the fascinating part. Of course, always an explosion is the fascinating part. It's fascinating. So then you have this core which collapses very quickly. Then it contains mostly neutrons and a bunch of neutrinos, so the smaller particles, neutrinos, which fly away. But wait a moment, there are some parts left over. First of all, there is this layer outside, very far away layer, which is still there. And then there is a part which is closer to the core, which didn't collapse. Now, suddenly this collapses as well, you know, the inner part, the outside part of the inner core collapses as well, but then it bounces off of the inner core, which is made of neutrons. And this inner core, which is made of neutrons, it has also a pressure this time. So this time, this inner core is able to sustain the gravitational pressure because the neutrons now are close to each other. And as we discussed yesterday, maybe I will mention that later, these neutrons, they also have a quantum degeneracy pressure. Okay, I will come back maybe later. But the point is that neutrons now, being very close to each other, is like, you know, people coming together and becoming stronger and stronger and stronger. They can keep up with the gravitational force. So the outer part of the inner core is going to come down on the inner part, and it really, within 1 second, reaches speeds up to 70,000 kilometers per second. So you can imagine 1, 2, 1, 2. After 1 second, it reaches speeds of 70,000 kilometers per second, and then it bounces on the inner core, and then comes back. It bounces out, and once it bounces out, you know, together with the neutrinos which are already coming out, they all go in the outside direction, but there they meet the outer layers, far away layers which didn't collapse yet, so they are standing there, and then they push these outer layers, and this is the explosion, what we see in the image. So I will go back to the video because I like the video.
So we can watch the video again, having a better understanding of what's happening on the inside to cause this reaction.
Yes, exactly. Yeah, I like, because this is the first one, and now remember what happens inside. So now inside you have this explosion. So the material which is bouncing out of the inner core, which is coming out, you know, coming out together with the neutrinos, and they push out all this material. Okay, laser pointer. Look, it is pushing out. The explosion is pushing out the outer layers, and these are the outer layers, faraway layers, which are pushed out, and that's what we see in the images. I'm going to show you an image. This is what we call a planetary nebula. So this is going to form a very nice view later, a planetary. And by the way, the star is very, very bright. The star may be brighter than a galaxy when this happens, really than a galaxy. And I have to say, now there is a lot of sound now, but it's nice. See the outer layers. This is the black hole. Okay, it was supposed to be a neutron star. But we have to know or remember that these things don't happen very often. there are explosions every few years, supernovae, even in our galaxy, but we don't see them because they are behind the stardust. I think about 50 years there is an explosion, supernova explosion in our galaxy, they say, but we don't see it because it's just behind some dust and so on and so forth. So only few percent of this we see. But we see supernova explosion in other galaxies because the light is shining like a galaxy. Okay, let me check the time. Okay, the time is good. So let's go, let me see. Okay, I have to share the screen again.
Yes.
Okay. This we talk.
Wonderful.
And this is a very nice nebulae, which happened. So the supernova explosion happened in about year 1100. And it was recorded by the Chinese astronomers, and actually not only by the Chinese astronomers, but even by the Chinese usual people. And they wrote in their books, like, there was a star which we saw even, you know, in the daytime for a few days. And then astronomers later, they looked at that portion of the sky and they discovered actually the nebulae. So what you see here are those remnants which were pushed away by the explosion. And this is what we see together, with the telescope. This is what we call, what is called Crab Nebula. And inside the Crab Nebula, there's a neutron star. As I told you, at the end of the day, the neutrons come very, very close together. The outer layers go away. So then you are left with a star made of neutrons, and we call that a neutron star. But the fascinating thing was that when people astronomers looked with the telescope at this nebulae, they saw that the remnant star, the neutron star, was still shining very brightly, even after about 1,000 years. And they didn't understand why is it so, because it wasn't supposed to be so bright after 1,000 years.
Right.
And actually, they found a solution only recently. And the solution is that there is a lot of X-ray radiation around the star after it's formed, few thousand years. And because of that X-ray radiation, the star is still very shiny, and we can see it also in invisible, and with X-ray machines even better.
Wow, so it's because of the radiation.
Yes, because of the radiation. Yeah, so you wouldn't be there. It's not good to be there.
Yeah, that's
it's
true.
Dangerous. X-ray is dangerous. So we all know that. Now, this is the remnant, the neutron star. And of course, this is an animation. Nobody saw that like this, but I like this animation because it has a few features. First of all, we have to say, and actually I have the second animation here. The neutron star is animating here if it would be above San Francisco. So what you see is that the neutron star has the size of a city. Remember, the white dwarf had the size of the Earth. This is even smaller. This is the size of a city, you know, few tens of kilometers. And in this neutron star, again, you find concentrated a mass of about 1.5, 1.6, or even 2 solar masses. That's all concentrated here because the neutrons are so close together. All the atoms are broken apart. And that's what you see here. Now, of course, if the star is very, very small, then the surface of on the top of the gravity, the gravity on the top, the gravity on the surface of the neutron star is very, very strong because the star is very, very small. And I found a calculation which I found interesting. If you take a ball and drop it from a height of 1 meter on the top of on the surface of the neutron star, so if you drop it from a height of 1 meter, then when the ball is going to hit the ground of the neutron star after 1 meter, it's going to have a speed of 7 million kilometers per hour. You know, so you wouldn't like to drop your spoon when you are in the kitchen on the neutron star, you know, and you eat something and suddenly you drop your spoon. The speed of the spoon when it's going to hit the ground is going to be 7 million kilometers per hour. It is crazy, insane. And that's
quite
what
a
we
force.
see. Sorry, Hida?
I said that's quite a force.
It's quite a force, yes, yes. And what you see here on the surface, these are tiny mountains, because you can imagine the star is only a few kilometers in size. And let me have actually here one maybe with atoms here, and I show you later. So because the gravitation is so large, then you cannot have mountains because everything is going to be flattened. Really, everything is going to be flattened. And I have this very, very nice picture of Tom. If he sits on the neutron star, it's just going to be flattened. And that's why the mountains here, they have heights of about 5 millimeters. These are the mountains of the neutron stars. This is what we see here, you know, like the small mountains. You know, they are just a few 5 millimeters. And then the atmosphere, you know, it's only about 10 centimeters high. So it's 10 centimeters, something like this. And this is the whole atmosphere. And at the top of the atmosphere, you're not going to find clouds. You're going to find plasma of electrons flowing around. So that's very, very strange atmosphere anyway. Okay, and of course, what would happen if you take a spoon of material of the neutron star? How much would that weigh, you know? How much would that weigh? And I actually have it here. It says here a few million tons. So a few million tons if you have a spoon of material of neutron star. So if you take an iron cube, like this here in this drawing, then you have a billion ton, like the Mount Everest, they say. So it's just a cube of material is heavier than the Everest mountain. But by the way, this is what I mean here is that if you take a spoon of neutron star and bring it, a neutron star material and bring it down to Earth, that would have millions of tons. If you would have, you know, iron cube of neutron star material and you would bring it with a ship on the Earth, then it would weigh, you know, like the Mount Everest. So it would be very difficult to keep it in the lab.
Yeah.
Now a little bit about the physics, because now the title of this presentation is the physics of compact stellar objects, or yeah, like neutron star. And what we see here, and this is not an animation. Yeah, actually this is an animation. This is a normal
kilometers a second as it collapses towards the.
Okay, so by the way, I put here YouTube links. If you want to watch them, I can also send them, because this is the nice part today. You find very good animations on the YouTube. But this is the normal star. This is the normal star where you have, you know, nuclei, and then you have the electrons flowing around. And at the end, you see the electrons are coming back because of course the core is push harder and harder. And the end, the electrons are going to come into the nuclei, are going to fuse with the protons, and are going to form mostly neutrons. And that's what we see here inside the neutron star. Now we have here the nuclei. So this, like, not round, but a square size shape. These are the nuclei. And you see here sometimes protons, sometimes neutrons, because they exchange. It's not like there's only neutrons. Sometimes the neutrons decay into proton and something else. And then sometimes a proton fuses with the electron and then again forms a neutron. So there is a kind of oscillation between the two. But the point is that they are close to each other. They are close to each other, and that actually gives you the size of the neutron star. Let me see if I have it here. Okay, I have it there, so I'm not going to tell you right now. What we see here, we see also that some electrons are flowing around. So let's look at the animation inside of the neutron.
Atom nuclei lattice with a sea of electrons flowing through them. The closer we get to the core, the more.
What? Okay, the second part was
atom nuclei lattice with a sea of electrons flowing through them.
Okay, so the closer you come to the core of the neutron star, you are going to find, of course, more neutrons and less electrons. But the point is that the electrons just fly around; they don't disappear, all of them. And from here we have basically the physics. of the neutron star. That means inside the neutron star, you have neutrons, and I'm going to switch again to me. Yeah, so inside the neutron star, we have the neutrons, and they are like in boxes. You remember when we discussed yesterday about the white dwarfs. In the white dwarfs, you have the electrons more or less in boxes, like 2 electrons, one spin up, one spin down, per orbital, or let's say per box. And those boxes have a size of 10 to the power minus 12 meter, which is the Compton wavelength of the electron. That means they are 100 times smaller than the atom, which gives you the size of the white dwarf. The white dwarf would be more or less 100 times smaller in size than the sun. That's why it's more or less like the Earth. Now, this time we have neutrons, and the neutrons, the same happens with neutrons. They also fermions. They also obey Pauli's principle. So they also need boxes. And you cannot put, again, more than 2 neutrons in a box, let's say in a kind of orbital. You cannot put more than 2 of them in the box. But now this time the boxes are smaller because the Compton wavelength of the proton is smaller, which is 10 to the minus 15 meter, which means it's more or less the size of the nuclei. So the Compton wavelength of the neutron is more or less what we consider the size of the nuclei, which is again 10 to the power minus 15 compared to the 10 to the power minus 12 from the electron. So it's 1,000 times smaller than the boxes of the electron. So again, the electron has a box like this, 100 times smaller than the atom. And then the boxes for the neutrons are 1,000, yes, and the boxes of, no, just to be sure. Okay, so you have the atom, the boxes of the electrons are 100 times smaller, and then the boxes of the neutrons are 1,000 times smaller than the ones from the electrons. Okay, so that means that the neutron star is 1,000 times smaller in size than the white dwarf. But the white dwarf was like the size of the Earth, 6,000 kilometers. You divide 6,000 by 100, gives you 60. So that means that the size of the neutron star is about 60 kilometers or something like this, 30 kilometers, 20 kilometers, but it's the size of the city. And then let me share again the screen. Okay, and then what I have here on the screen, actually had the curiosity to see how much I would weigh on the neutron star. Because when you sit on the neutron star, the gravitation force is so strong because you are closer to the center. This is very important, and I have time to tell that. Because it's very interesting. So you see, the fact that the gravitation is very, very strong on the neutron star, it's not related to the mass of the neutron star, because the mass of the neutron star is the same of the mass of the sun. But with the fact that the neutron star is very, very compact. And remember, the force of gravity is stronger and stronger and stronger if the two things are very close to each other. The force of gravity depends on the distance with the 1 over square of the distance. That's why when you sit on the top of the neutron star, you are attracted gravitationally very strongly by the neutron star because you are very, very close to it. Not only because the star has a lot of mass, which is the mass of the sun, but also because the distance is very small and the force is 1 over square of the distance. So then the force becomes very, very large. Okay, so that's why you weigh so much on the neutron star, because you are attracted very strongly. And I had the curiosity to calculate my weight on a neutron star, and I found actually that I weigh about 9,800 billions kilograms. So it's no point in living on a neutron star and following a diet.
Just a wee bit more.
Yeah, indeed. There is a question. I saw a question somewhere. Because then I have to move to the second part, is how we detected the neutron stars. And I'm going to talk about gravitational waves, and I have some animations. So now it's going to be like less physics, but still some physics with a little bit more animation. So now listen to a neutron star. You see, it's like you listen to a broken car. There is some boom, 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 boom. Why is happening?
Yeah, it's like a motor.
Like a motor, exactly, but not a very good motor.
Yeah,
I hardly have a better car.
Motor. A motor that needs work.
Exactly. That needs repairing. And why is that? Well, that is because the neutron stars are also pulsars. I think you say in English pulsar. Yeah. How do you say in English?
Pulses.
Pulses, yeah. Pulsars. Okay, so let's see the second video.
From the colossal explosion falls back to the pulsar and forms a disk. Within this chaos, a new world arises, born of fire and destruction. A planetary zombie raised from the carcass of the former red giant star.
You see, you saw also here like the planetary zombie, the planet which is still orbiting around, which survived the explosion in this animation. But the most important part is this one here. What you see here, you see a beam of light which is going around. So I'm going to switch to me for clarity, because what happens is the following: the neutron star. Maybe have here somehow. Let me see. No, I don't have it here. Okay. Oops. Ah, that was the crash.
I still see you.
Oh, you still see me? I thought it was the crash.
No, we still see you. No crash.
Yeah, but there is a crash because my my computer is not reacting.
Oh, okay. Well, your camera's still working, but
my camera is still working.
You mean your presentation has disappeared?
Yes, my presentation is just stops and I
became a supernova.
Yeah, exactly. And I think that my computer may crash as well.
Okay.
But okay, I'm going to talk you. One moment, if you bear me with a minute.
No worries.
Okay. You can still see me, yes?
I can still see you. Yeah, we can still see you.
I have no reaction from the computer. Okay.
If you want to, maybe we can. If you need to get off and leave the call and then maybe relaunch.
I don't think this is going to help my computer. I think that the best way is just to move to the other computer.
Okay.
Okay, let me finish this one here, and then we move to the other computer.
No problem.
So the point was that the following: I wanted to show you kind of image of the pulsar, and I wanted to show you that the pulsar rotates. And what is the pulsar actually? It's a neutron star which rotates very, very fast. Actually, all neutron stars rotate very, very fast. That's because they form from the star, the original star. And the original star rotates always. I would have to say always. Every star rotates, you know, around his axis here. And when the core collapses, the core continues to rotate, but it's going to rotate even faster. You know, when you saw this dancer on the ice skaters, when they go around and they put their hands like this, they rotate even faster because the angular momentum increases. And that happens with the core. So the core, when it forms, rotates even faster. So the neutron star, when it's left over, rotates very, very fast. You can still see me, Heather, yes? No, not anymore?
Yes. Yes, I can still see you.
Okay, okay. So then the core rotates very, very fast. Now what happens is the following. The neutron star is also a magnet at the same time, like Earth is a magnet. And the Earth is a magnet, and it has magnetic North Pole and magnetic South Pole. And for the Earth, the magnetic North Pole is more or less aligned with the geometric North Pole. That's why you know, you can go to the North a geographical pole, you know, by using the magnet. It has to, because the two are more or less the same. So the geographical pole is how the Earth rotates, and the magnetic pole is where is the magnetic field. But for the neutron star, it's not the same. And actually also for Earth in many thousands of years, the magnetic north pole is going to change. So that is in the neutron star most of the time. That means that the magnetic north pole of neutron star is not aligned with the geometry or with the geographical pole.
Yeah,
and that
I
means,
understand.
and that means that the neutron star is a kind of light tower. It has this magnetic pole, and at the magnetic pole there is a lot of radio waves, and it becomes like a light tower which goes around. Say, Heather.
Yeah. So Mihai said that your screen was frozen on his end. The screen was frozen, so it might be good for you to hop on the other computer.
Yes. So kick me out of here, and I move to the other
Zoom
computer.
here, and we'll open up. You should be able to just get use your link. The same link.
I'm already trying to do this. Let me see.
I'm not sure how to disconnect. Let's see. And it should open you up on there.
Okay, I think I'm on the other computer already.
Oh, there you are.
So you have to stop me.
I see. Now we see you in two. Well, I see you in two directions, but I think everyone else sees you in one direction. But let me check.
No, this is a proof of the existence of the multiverse.
Exactly.
And the parallel worlds of Everett.
Exactly. He said he was going to disconnect you. Okay. There we go.
Okay. So now you can see me?
Okay. So yes, I can see you just fine.
Can you hear me?
Yes.
Okay. I have like 15 minutes left, so I'll go faster through the rest of the presentation. And let me
back
see
live, so you're good.
If I save here the PDF file. Okay, fortunately I have the PDF file. So now I do here a share screen. Okay. I have an echo. I don't know if it's coming from me.
Yeah, it seems it's from the echo created with other device which gets stuck, and I cannot even
I have a very
out.
short solution to that.
Close the lid.
No electricity, no artificial intelligence.
That's great.
Everybody's afraid of artificial intelligence. I solved it. Okay, so then let's do the last 5 minutes. I have a PDF presentation, so here there are no there are no animations. Well, actually, let's try. Maybe on this computer I don't have a neutron star. Okay, maybe here I don't have the problem. Okay, you can see my my screen, yes?
Yes.
Okay, so I'm talking here about neutron star fusion. These are the two neutron stars which came together, and they start to fuse. You know, and then of course you have very, very nice explosion at the end. And what I want to talk here about is how did people measure a neutron star fusion with the help of the gravitational waves. This is what I want to show here. And the first thing we have to understand is that neutron star, they sit in space. Okay, let me start again the screen so that we have sound. Okay, and here we should hear the animation, the sound.
I don't hear the sound, but I can see. Oh, yes, I do.
The more mass, the more that space gets bent and distorted by gravity. For example, the reason the Earth goes around the Sun is that the Sun is very massive, causing a big distortion of the space around it. If you just try to move in a straight line around such a big distortion, you will find yourself actually moving in a circle. That's how orbits work. There's not an actual force pulling the planets around, just a bending of the space. Gravitational waves are produced whenever masses accelerate, changing the distortion of space. Everything with mass and/or energy can make gravitational waves. If you and I started to dance around each other, we would also cause ripples in the fabric of space and time, but these would be extremely small, practically undetectable. Now, gravity is very weak in the scale of other forces in the universe, so you need something really, really massive moving very, very fast to make the big ripple.
Okay, so the idea was clear here, and I have here the link if you want to watch the whole YouTube video. Actually, here somehow I missed the link. Maybe that's the next one. But one moment, yes. So the idea is that the space is like a fabric, and once you sit in space, it's like you are sitting on the fabric. So you deform the fabric. And the point is that neutron stars are really compact, and because they are very compact and they have a very high mass, they deform very much this space around. And then when they start to fuse by going around each other, then this distortion goes away like some waves in the fabric of space-time, and this is what we measure. So this is what you see in the next animation, these waves in the space-time. You see here? So you see here two, they can also be two black holes, and they go around each other and they create these waves in the fabric of space. And the closer they get, the higher the waves. The last moment is the best moment of detection, because then the waves are very, very, very high. How did we measure that? How did we measure the gravitational waves? Now I have this is the link of the very nice YouTube video. And you should have sound as well.
Points get stretched, then light will take longer to go from one point to the other. And if the space gets squeezed, light takes less time to cross the 2 points. This is where the Ligo experiment comes in. It has 4-kilometer-long tunnels and uses lasers to measure the changes in the distance between the ends of the tunnels. When a gravitational wave comes through, it stretches space in one direction and squeezes space in the other direction. By measuring the interference of the lasers as they bounce between the different points, physicists can measure very precisely whether the space in between has stretched or compressed.
Okay, so I really like this presentation because it tells you the basics. I cannot tell you better than this. This is so nice indeed. The wave, the gravitational wave, which stretches the space, it has this type it's like a texture. When you pull it one way, you stretch it in this way, it becomes shorter in this way. So that's how they design this gravitational wave detectors with these two lasers, because the space is stretched in one direction, is larger in one direction and shorter in the opposite direction. If they see that, they know for sure that there was a gravitational wave. And they had this 3 kind of detections, and they were able to detect the gravitational wave coming from the neutron star. Okay. And this is the sound of neutron star fusion. Somebody make this, and I also like this. This is not like, you don't have to think that this is the real sound. No, these are gravitational waves, and they are like then interpreted as sound. So there is a kind of signal processing done so that you can hear the gravitational wave, but of course you can never hear the gravitational waves. So now the neutron star oscillate. Now you are going to hear faster and faster.
As they get closer. closer.
And they get closer, indeed. And then they are going to fuse. Okay, and this is the fusion. And this is the last slide of the presentation before taking some questions. Actually, this slide here got the Nobel Prize because it was the first detection of the gravitational waves. There was a fusion, and I have to remember, I don't know for sure if in these graphs we have neutron star fusion, of black hole fusion, of a fusion between a black hole and the neutron stars, because they're not so difficult to discern. They are kind of, yeah, it's a little bit difficult to know which it was. So I don't know for this slide what it was, but I know for sure that this got the Nobel Prize. And what we see here, you see here time on the horizontal part. You see frequency on the top part. This is the frequency of the sound which we heard, which is basically the frequency of the gravitational waves which we see. And you see two LIGO detectors, one in Livingston, the other one in Hanford. And if you look at the oscillation, you see that the frequency, you know, there is an oscillation here. And the amplitude of the oscillation increases. The data is a little bit noisy, but between the two devices, which they made the measurements completely independently, there is a higher, very, very high accuracy. So this is for real. And of course, because it is for real, people deserve to get the Nobel Prize. And this is actually the end of my presentation.
I know everyone's clapping out loud. Wonderful. Very interesting to see the frequencies of the waves and to be able to hear it, and as well the innards of space, the music of space, to be able to hear that. I love that. Okay, let's see. Mihai, you're here, and we can look at the Q&A. Can you see the Q&A?
Yes, I can see the Q&A. So I have a question. Can a neutron star be dangerous to us? The point is, if the neutron star is like far away, you know, it's like, let's say that there is a neutron star orbiting around the sun at the same orbit as Jupiter or as Pluto. Then it's not dangerous. Of course, if it is the neutron star, if it doesn't have, you know, X-rays around and so on and so forth. If it is a neutron star, which is quiet, because after many millions of years, then the neutron stars, if they don't have matter to enter into it, they may become kind of quiet. But I'm thinking right now, if the neutron star have this radio waves, and if the radio waves, they go out of the poles, I'm not so sure actually, but in the first instance, I would have to say that maybe it's not dangerous if it is far away on the orbit of Pluto. Of course, it is very close, that's a different matter, but on the orbit of Pluto, maybe not. But I'm thinking right now that indeed you have this still magnetic phenomena, which are very strong on the neutron star. And that's why you have radio waves, that's why you have magnetic, you know, explosions. So it could be that actually that is dangerous, because if you have a magnetic storm around the neutron star, even if it is on the orbit of Pluto, it may influence all the electromagnetic devices which you have here.
Yeah,
yes.
I was going to add to that it seems like if even our planets that are closer to us can influence us, or the sun with its pulses and radiation, of course, you know, can influence us, then I even imagine that things even outside of our sight, or out of our solar system, or could also impact us in ways that we are maybe not even aware of, or maybe we just can't measure at this moment.
Yeah, I kind of agree with you, even though I have to add that the neutron stars and all the objects become more active if they have material to feed into it. So we see many neutron stars which are very active outside because they feed with matter from surrounding. But if you would have like a neutron star which is not fed with anything, just by itself, then maybe it's less dangerous. But I agree with you, it's still dangerous. I think it's still with this magnetic you know, storms is not nice when we have internet, and then suddenly, you know, everything drops down. No internet
True,
today.
but they make beautiful skies for way up north, though.
Yeah.
With the lights, that's for sure. Okay, I see more questions.
I have here. Do neutron stars ever die on their own? If they do, what happens when the neutron star dies? Well, I have to remember because in principle, a neutron star should die because the neutron star is made of neutrons mostly. And they always, you know, disintegrate into protons and electrons and neutrinos and so on, antineutrinos, I think. Yes, protons, electrons, and antineutrinos. And the antineutrinos fly off. And then I think that the neutron star disintegrate in time. But on the other hand, I think everything depends if the proton disintegrate. Because the neutrons are made to disintegrate, you have more protons, but we don't know yet if the proton disintegrate. The proton is at the moment a very, very, very stable particle. So actually, I'm afraid I cannot answer to your question, which may happen.
A good question.
Yes, good question. Okay, I think we are at the end of the presentation.
There's one more question here. Oh,
okay.
Maybe it's the same question. Can a neutron star be destroyed? Oh, yeah, you kind of answered that one.
Yeah.
Well, since energy just kind of re-extinguishes itself in a different way, it's never quite destroyed. It just changes
to somebody.
Yeah.
Yeah. But remember the discussion of yesterday. Let's hope it doesn't change the black hole, because kind of, and even black hole does it because
exactly.
of Hawking radiation.
Yeah,
so everything changes into something else, like during our lifetime into something else.
That's right. It's just constantly evolving. That's all. So when is the next presentation to share with everybody? When are we going to
I think you have to send in the invitation, but I think it's tomorrow at the same time.
Okay,
the
wonderful.
same hour. I'm not so sure.
It's tomorrow, 7:30 Romanian time, 16:30 UTC.
So it's the same time as today?
Yes, same time as today, correct.
Okay.
And people can check the website for that. We'll keep everyone posted, but that's when we're going to dive into black holes, right?
Yeah, exactly. Yeah, hopefully
we're looking forward to that. I want to thank you so much, and everyone that joined us, and all our Facebook Live watchers too. We're looking forward to tomorrow, and thank you for being a part of the Atlantykron Virtual 2020. Appreciate it.
Okay, you're welcome.
We're going to wish you a pleasant evening.
Yeah, have a nice
evening.
Bye. See you.
Bye.
Goodbye.
Bye. Bye-bye.